So we'll talk about adding and subtracting rational expressions. And the theory behind this is exactly the same as when you have just regular fractions, that if we already have a common denominator, we're going to just add or subtract the numerators. And if we don't have a common denominator, then we're going to make them common. So let's look at a few cases where we already have the common denominator. The first case is where we just have x over 10 plus x plus 2 over 10. And so we get that x plus 2 over 10, and so that turns out to be 2x plus 2. Now we can simplify that a little bit more, and so here what we have to do when we're looking at these, once we combine them, there's a good chance that we may be able to reduce this fraction. Just like you would reduce 2/10, you have to first factor out the common factors, and then you can cancel factors. And so let me emphasize, you don't factor by terms, or excuse me, you don't cancel by terms. What you're really doing is you have to factor this out, so when you're canceling, these are products, 2 times 5 and then 2 times x plus 1. A lot of people will make the mistake that they'll either cancel one or the other of these terms that are in a sum, and you really have to do both of them. And so the safe way to do this is to write it as first a factorization and then cancel it. Okay, so here's one, has a common denominator of n times n plus 2. And so the tricky part here is to remember that when you are subtracting, that the negative applies to the whole polynomial that's in the numerator here. And so the safe way to do this is to write this in parentheses, so you can kind of keep track here of the fact that you have this negative that's going to change that negative to a positive. So when we expand this, we can just remove the first parentheses. In fact, you don't have to put them there if you don't want to. But the second one, we do have to distribute that negative, so it becomes negative 1 plus 3n, and then we can simplify it. And if we look at how this simplifies, we have 3 minus 1 is 2, and then negative 2n plus 3n equals just n. And then you see this is the same thing. This n plus 2 is the same thing as this n plus 2 down here. It's just commuted. So we're just going to end up with 1 over n. And of course, we always have to consider what the domain restrictions are. And in this case, that since we're dropping that factor n plus 2, we know that n does not equal negative 2. All right, everybody with me here? Okay, so let's talk about now making common denominators. And so what we want to do is use the least common multiple of the denominators. Oftentimes when you're dealing with numbers, it's just more expedient to just take the product of the two denominators and then essentially multiply the two numerators by those denominators to make a common denominator. If you're doing that with polynomials, what happens is you really start getting a whole lot more factors than you need. So when you have something like this, where and these squiggles just mean I'm not paying attention to the numerators here. I'm just looking at the denominators. When we have 20 and 12, you might be tempted to make the common denominator of 120. But if you really look at what's the least common multiple here, you have 20 factors into 2 times 2 times 5 and 12 factors into 2 times 2 times 3. So the least common multiple, you notice they both have a 2 times 2, so you only use that once. And then you have the unique factors of 3 and 5. And so the least common multiple is 60. So a better common denominator then is 60. Now the same thing when you have polynomials in the denominator. Here if we have x times x plus 2, and here we have x plus 1 times x plus 2, we only use the x plus 2 once. And since that's in common, and then the unique factors for each part are going to be x and x plus 1. So your least common multiple is going to be those three terms. Yes.
So for the blue
Yes.
equation, 2 times 2 is 4, right? So
Yeah.
why is it 60?
Well, 2 times 2 is 4, times 3 times 5 is 60. The reason why I put the bracket here is because these are common with both of these. Okay, so really the least common multiple, what I intended here really to show is that it's 2 times 2 times 3 times 5. Okay, I'm just highlighting the 2 times 2 because that's in common with both
So if they have
of the
one in
fractions.
common,
So
then you
wouldn't the
can do it.
LCM just be 4?
The LCM is not 4. Between 20 and, that's the greatest common divisor. Okay? So think about what you're saying. The least common multiple is, if we break it down to what are the multiples of 20? The multiples of 20 are 20, 40, 60, 80, 100, 120, and so on. The multiples of 12 are 12, 24, 36, 48, and so on. And so what we're looking for is, what do they have in common? Well, they both have 60 in common, and that's the lowest of the least common multiples. 120 is still a common multiple between two of them, but it's just not the least one. Okay, what you're perhaps thinking is the greatest common factor. Well, when you look at the factors here, if you factor this, the one that's in common is the 2 times 2. So the greatest common factor, the GCF, is 4, but we're looking at the least common multiple here.
Okay, and then does it matter if you bracket off the 2 that are similar, or the 2 that match?
Well, the bracket is just for my illustrations purposes. All you do is you take the 2 times 2 times 3 times 5. You take the common multiples, multiply it by the unique, or the common factors, and you multiply it by the unique factors of each.
So you can do that when they've got a common multiple. But you can't do it if they didn't have anything.
If they didn't have anything in common, then you would just multiply both of them together.
Okay.
Okay? Just like if you were adding 2/7 and 3/5 together, the common denominator would be 35. Okay, so between these two, if you have these as the denominator in a fraction, what's the least common multiple? Try that.
How did you get the second one?
The second one, I looked at what's in common, which is the x plus 2, and then I multiplied it by what's unique.
Mr. DuBois,
Yes.
he's thinking some other fractions AM squared 45.
Well, I'm talking about these as being the denominators of two fractions. I'm just giving you two numbers and asking you for the least common multiple. So if they were the denominators of fractions, what would be the common denominator is really a rephrasing of that. Yes?
When you do the LCM, like for example, the one in the green, you have 2x plus 2's. You only take out one of them just to represent the x plus 2's.
Yeah, because they're in common. So you only use the ones that are in common once. Okay, anybody get a LCM? Jazzy? It would be 9m. Okay, now the least common multiple would be larger than both. I think what you found was the greatest common factor. Okay? Who else had one? Magali, did you? 90.
I just got 90 as the least common multiple.
Yeah, 90 for the coefficients, but what about for the, is it m or m squared? M squared, right? Okay, so let's look at y. Okay, we're going to factor this first one. 18m squared is 2 times 3 squared times m squared. And then 45 is 3 squared times 5 times m. And so what's in common here is the 3 squared and the m, but we also have a unique factor in an m for the first one. So let me write this a little differently. If I were to write this by expanding it out, so 18m squared is going to be 2 times 3 times 3 times m times m. So I'm not using any exponents. And then 45m is going to be 3 times 3 times 5 times m. So when I look for the common, what's in common, I have these 2 3's in common, and I have these 2 3's in common. So then you're going to take 3 times 3, and then you're going to take all the unique factors, all the remaining ones. So we have and this m is common. So we have 3 times 3 times m, which are your common factors. So now what you do is you take the unique factors, which are 2, 5, and m, and you multiply 2 times 5 times m. And so when we gather up the terms, we have 9 times 10 is 90, and we have m squared. Okay, does that make a little bit more sense? Okay, so when we're adding with unlike denominators, we find that least common multiple, and then we have to do something to the numerator too. So let me go back to having just a numeric denominator. We found that the least common multiple is 60. All right, so what I want to do is I want to say, all right, with my 5x over 12, in order to make this 12 a 60, I'm multiplying it by 5. And so I don't want to change the value of it, so I'm multiplying it by 5 over 5, which is 1. And then in the second term, what I do is I ask myself, okay, how do I go from 20 to 60? Well, I multiply by 3, and so I'm going to have to change the numerator as well, so I'm not changing the overall value to being 3 over 3. And then when I multiply those out, I get 25 plus 9 over 60. So now the question is, can I reduce that? And the answer to this one is no, because the numerator, all you can factor out of the first term is, it's 5 times x. Second one is 3 times 3. So there's nothing in common, nothing to factor out, so you have nothing to cancel with any of the factors that will be in the denominator. Okay, so now let's look at one that has a polynomial in the denominator. So the first thing that we want to do with this one, so we can identify what the LCM is that we want to factor the denominator. And so we look at x squared minus 1 as being x plus 1 times x minus 1, and we look at x squared plus 2x plus 1 as x plus 1 squared. Okay, so now we need to identify the least common multiple. We have an x plus 1 that's in common between the two of them, and then the unique factors are x minus 1 and that other x plus 1 that's in the other denominator. So we have x minus 1 times x squared, or x plus 1 squared. So we'll set this out to be, okay, the first one, what we have to do is we have to multiply this by x plus 1 over x plus 1. On the second one, what we have to do is multiply it by x minus 1 over x minus 1. And so now the denominators are the same, and we've multiplied the numerators by whatever factor it took to transform that denominator into the common denominator. All right, then we can just add the numerators. And notice what I did here. I've expanded both of them. So I have that 5x times x plus 1 is 5x squared plus 5. That should be 5x, right? Yeah, I have made a mistake here. So let me make a correction here. So this should be 5x plus 3x minus 3. And then I probably made a boo-boo here too. Yeah, this should be let me change this to be this is actually should be 8x, and then this one here is going to be still -3. So now the question is, can we factor that? Okay, so let's see how we can factor this, if it does factor. We have 5x squared plus 8x minus 3, and so we take the 5 times 3 is -15, and so the factors of, we know these have to be opposite now, so we're looking at what makes 8, and so if we say the biggest one is going to be 15 times -1, that's going to be, add those two together and we get 14, and then the next one is going to be what, 5 and -3, and that's going to be 2, and then we have that's it, it's going to be 3 and 1. And so neither of these equal 8, and so we know that that's prime then. There's no more canceling. Oops. So we're done there. Okay, any questions before I have you try a couple? Okay, so here's for you to try. And so with these, well, we'll see how it goes. Okay, so there's our 3 answers. And since there was no cancellations, no factors lost, everything in the denominator stayed in the denominator, there was no domain restrictions that we needed to note. All right, everybody get these? Can I go on? Okay, so let's try a few more. Okay, so first on the notes. Okay, that's what we had on the board. And then the second one is 6x minus 1. Now this next one, what we want to do is first factor the denominators. And so recognize here that the x squared plus xy, this one has a greatest, this one has that common monomial factor of x, and so we can factor out x there. This is the same thing except that it has y common between the two of them. And now we look at what the denominator is. Now notice here that we have both of them have x plus y, so that's the common factor, and then the unique factors are x and y. So our common denominator is going to be, it's going a little too far. Anyway, our common denominator is going to be xy, x plus y. So since we had to multiply this one by x, we have to multiply that x times x. And since we have to multiply this one by y, we'll have y over y, and so we have y squared minus x squared. Now, x or y squared minus x squared factors into y minus x and y plus x, and we have a y or an x plus y here, and so these two cancel, and so we get y minus x over xy. And So we did lose one of the factors. We lost this x plus y, so we have to make sure that x does not equal negative y, and that's the way we avoid the 0 in the denominator. Okay, so it's a little bit more involved, that one, but it has, first you make the common denominator, and then you combine all the terms in the numerator, see if it factors. In this case it did, and then we cancel out common factors, and when we cancel common factors, we have to note the domain restrictions.
How did you get the y squared minus x squared?
This one here?
Yeah.
Because what I'm doing is, in order to get this denominator is just x times x plus y, so I have to multiply this times y over y to get xy times x plus y. And then on this one, I have to multiply it by x over x.
Okay.
And so since this is negative, I have y squared minus x squared.
Okay.
And since that's the difference between squares, we go for it. Okay.
Does it matter if it's x minus y or y minus x?
No, certainly x does not equal negative y, or y does not equal negative x says the same thing. Okay, so now what I want to talk about are complex fractions. And so what I mean by a complex fraction is when you have a fraction in the numerator, a fraction in the denominator, and then you have this kind of main fraction in between. Okay, and so we'll deal with these much in the same way that we were doing division between two rational expressions. The thing that we want to do here is, if we have an opportunity to simplify the numerator and the denominator fractions first, that's a good thing. And then we'll take the numerator times the reciprocal of the denominator to simplify this out. Okay, so here's an example if we're going to do it with just numbers. Okay, so we have 1/2 divided by 3/5. And so that's 1/2 times 5/3. So I've taken the reciprocal of this denominator ratio, and so now I can take 5 times 1 is 5, 2 times 3 is 6, and I get 5/6. Okay, so that's the basis for everything we're doing with complex fractions here. So let's look at one that involves some polynomial expressions now. This one is the first one here. So what I'm going to do is I'm going to take this x plus 1 over x minus 2 as the first term, and then that denominator fraction or ratio, I'm going to take the reciprocal of this, which is x over x plus 4, and I'm going to multiply them, and so I get my ratio. So let me make sure that it's clear that this is the same as this now. Okay, so let's look at a couple here. Now, domain restrictions are the same as we've had before, where we have domain restrictions on 3 of the values. So we can't have b equals 0 because then we have division by 0. We can't have d 0 because then we'd have division by 0 in this denominator. Now c can't be 0 because then we're making the overall division, the division that's expressed by this middle line here. If c was 0, then we'd have division by 0 again. So there's 3 places, just like before, where we can't have 0. And so the only value of this whole ratio here, a is allowed to be 0, because then you'd get the whole thing equals 0. If you have 0 in any other position, you have division by 0, and that's not defined. Okay, so let's look at one here. So when I have this complex fraction of x plus 1 over x plus 2, and then x plus 1 over x plus 5, I'm going to take the numerator fraction and then multiply it by the reciprocal of the denominator fraction, and then I'm going to combine them. Now notice I can cancel out the x plus 1's, and so I'm going to get x plus 5 over x plus 2. Now, we still need to put in the domain restrictions, and we're going to have, what is it? Negative 1, because you've canceled out this, and if x is negative 1, we'd have division by 0. Is there any other domain restriction that we have here? Excuse me? Well, there's one that's implied, which is the x does not equal negative 2, but there's one that we need to write still. Negative 5, right? Because in this case, we can't have division by 0 for this ratio, even though when we take the reciprocal, you know, it suggests that perhaps we could. But since that comes from the denominator here, x does not equal negative 5. So you have to look at the original fraction and say, okay, x plus 2 shouldn't be 0, and that one's still implied. X plus 1 can't be 0, that's no longer implied, so we have to state it explicitly. And then x plus 5, that is in the numerator, so we do have to call that x does not equal negative 5. Okay, so try simplifying these two. So let's see how these go. So it isn't obvious, well, there really isn't anything that we can do to simplify the fraction in the numerator. Nothing that we can do to simplify the fraction in the denominator. So we'll rewrite these as just the product of these two ratios. And then we start looking for factors that we can cancel. And we notice that we have the 36 divided by 9, which is 4, and 20 divided by 5 is 4. So 4 times 4 gives us a 16. We have an x to the 4th divided by an x, and so that makes x to the 3rd. And then in the y's, we have a y to the 4th times y squared makes y to the 6th in the denominator, and we have a z to the 5th in the numerator, z to the 5th in the denominator, so those cancel out, and so those go away. And so now we have to look at what's the domain restrictions. So the first one is that x can't be 0, right? Because if x is 0, we'd have division by 0 because of this 9xy squared. Okay, so then we ask ourselves, how about the y? Well, z can't equal 0. Z dropped out because we completely dropped that. And of course, z can't be in either of these denominators. Z can't be 0. And then the last one, of course, is, ooh, did I not write the y is implied. Okay, the y, since that's in the denominator, is implied. So we don't have to write that one. You could write it if you wanted to, but not necessary. Okay, now on this next one, we have the same thing again, where the numerator, y over 3 minus y can't be canceled, it can't be reduced. Y squared over y minus 3 can't be reduced. So we'll write that then as a product of the numerator times the reciprocal of the denominator, so that's y minus 3 over y. And then the y's cancel out. This y with this y squared leaves us a y in the denominator. Then we have y minus 3 and 3 minus y. So we can factor out a negative 1 and cancel out the y minus 3. Just recognize that that's negative. So that's where I get my negative sign. And then it's a matter of, what are my domain restrictions? Whoops. Y can't be 3, because if it was 3, we'd have division by 0 here and here, and that can't be. So it's also implied that y can't be 0, because then we'd be dividing by 0 because of that y squared being 0. Yes?
Doesn't the y
It does, the y and the y squared doesn't completely cancel, it just cancels to y.
Because you do, so you have y minus 3 on top. And then doesn't it, you factor out the negative 1, so that's another y minus 3, so those cancel out.
Yeah.
Oh, wait, hold on.
So there is no y minus 3 anymore. It's just that negative. And then we're left with the y over y squared. Yeah, put your homework up here, right where Carolyn has hers.